Open any standard calculus syllabus, and you are immediately hit with a wall of noise. Dozens of rules, inverse functions, and expanding identities appear to pile up without an end in sight. Many students attempt to process this by treating calculus as a vocabulary test, spending hours trying to force 100 disconnected formulas into short-term memory through pure repetition. However, calculus operates on a single continuous logical pathway. The system is a dual-directional engine. Every operation in the course involves either moving forward to calculate a precise slope or running backward to reverse that process. Navigating this machine relies on a strict cascaded hierarchy. You build the system in stages, establishing the most basic axioms at stage 1, and then layering those same rules to solve the complex functions found at stage 6. Understanding the architecture connecting these stages makes complex formulas a predictable result of simpler rules. We begin by building the forward-moving half of the machine, differentiation. This graph plots a toy car moving along a curved road. Differentiation measures instantaneous change, tracking how quickly your y-axis position shifts as the x-coordinate changes. We track this through geometric steepness. Uphill is positive, downhill is negative, and perfectly flat is 0. This rate of change is represented by the formal notation dy over dx. The simplest input for this machine is the variable x. If x increases by 1 unit, its rate of change is naturally 1. For more complicated algebraic inputs, we use the primary tool of the hierarchy, the power rule. To process the term x to the 5th power, the exponent drops down to the front multiplier position, and the remaining exponent takes down by 1. The output is 5x to the 4th power. Differentiation acts as a geometric magnifying glass, isolating the precise steepness of a system at any specific point. At stage 2 of the hierarchy, the machine calculates what happens when multiple interacting variables change simultaneously. Take the function y equals x squared times sine of x. We have an algebraic term multiplying a trigonometric term, with both shifting at the same time. This graphic demonstrates the logic of the product rule. Imagine inventory defined as the number of boxes, U, times the apples inside each box, V. The total number of boxes can fluctuate, but the amount of apples packed inside each box can also change independently. To measure the total change in inventory, you must calculate both shifts. We map this logic into the formal product rule formula. For x squared sine x, we break the equation into its constituent parts, slop them into the structure, and arrive at the final derivative, x squared cosine x plus 2x sine x. These complex equations are assemblies of stage 1 components slotted into stage 2 combination rules. We now turn the calculus machine around to access its second primary function, integration. To integrate is to reverse the differentiation process, taking the fractured pieces of a derivative to rebuild the original function. This reverse engineering process faces a specific challenge. Differentiation removes constant data from the equation. Because a constant number never changes, its rate of change is 0. It vanishes during the forward process. This diagram plots 3 parallel parabolas, y equals x squared, y equals x squared plus 5, and y equals x squared minus 100. Despite having different vertical positions, all 3 share the exact same steepness profile and output the identical derivative, 2x. This creates a directional information gap. Feeding 2x backward, the system cannot identify which original parabola generated that slope. To document this, we use a placeholder. We integrate 2x to get x squared and append a plus c. That c represents an infinite vertical family of parallel functions that could have generated the derivative. While differentiation removes static data, integration uses plus c to map the boundaries of the information that was lost. We can expand the machine to process a different data domain, the trigonometric ecosystem. The 6 primary trigonometric functions provide specific geometric ratios for measuring angles. These follow strict geometric origins. The basic SOH-CAH-TOA ratios lead to identities like sine squared plus cosine squared equals 1. These identities feed directly into the same slope-finding machine we have already built. These formulas define the cyclic relationship of trigonometric derivatives. The derivative of sine is cosine. And the derivative of cosine is negative sine. The most critical nuance here is the minus sign in the cosine derivative, a frequent point of error. Trigonometric calculus is simply the exact same algebraic rate of change engine seamlessly applied to spinning, rotating geometric shapes. We can now bring these components together to run a closed-loop test of the calculus machine. We will integrate the polynomial 6x squared plus 4x plus 3 by separating it into 3 distinct operations. Using the reverse power rule, the first term yields 2x cubed, the second yields 2x squared, and the constant 3 becomes 3x. We include the plus c to complete the reconstruction. We feed this result back into the forward engine. By taking its derivative, the terms shift and collapse back into the original 6x squared plus 4x plus 3. The learning strategy is a sequence. Master the foundational constants, learn the combination structures, grasp reverse engineering, and then layer in trigonometry. This roadmap shows the exact progression needed to operate the system. The first pillar is that the derivative always equals slope. The second derivative dictates the change of that slope, and the integral is the precise reverse of differentiation. Navigating this interconnected machine provides the logic necessary to solve problems across the entire calculus landscape.